Fernando, but shall we try also you sharing the presentation? Hi, Slinger.
Hello, Slinger.
Yeah, we also have started the recording, I can see. Right.
Yes.
So would you like to share your slides, Fernando?
Sure.
Okay, we can see it. Perfect. So let me welcome Fernando Castor for today's colloquium. He's an assistant professor in our department and also an associate professor on leave in the Informatics Center of Federal University of Pernambuco in Brazil. Between 2019 and 2020, he was a visiting professor at Professor Hidehiko Masuhara's group at Tokyo Institute of Technology. And before, he also worked at the University of Sao Paulo, University of Newcastle, University of Kent, at Canterbury, at Lancaster University, and at Microsoft. His broad research goal is to help developers build more efficient software systems, but he worked on a variety of subjects, such as program transformation systems, formal modeling of exception propagation in sequential and concurrent systems, failure detection in distributed systems, aspect-oriented programming, and design diversity in service-oriented architectures. So today's talk will be on improving energy efficiency by recommending Java collections, and energy efficiency, of course, became extremely important with these large models. Maybe you will remember last year's scandal about the deep models on natural language processing and Timnit Gebru's firing and all the controversies surrounding that. So we're very happy to have you, and the floor is yours.
Thank you, Albert. Yes, as you folks can see, I have a very hard time focusing. This is work that was developed in cooperation with Wellington, who is currently at University of Lisboa, Renato and Benito, who used to be my master's students, Gustavo, who is an assistant professor at Federal University of Pará in Brazil, and João Paulo, who is an associate professor at Universidade do Porto in Portugal. And yes, as Albert mentioned, today I'm here to talk about energy. It's one of my favorite topics. And energy is pretty important, and not just for me, but for consumers and for users of smartphones. Again and again, consumer research has shown that long battery life, it ranks very high amongst the most desired features from smartphone users. It's usually the most desired feature. I've seen this again and again, but it's important not only for smartphones, but also for desktop applications, for desktops, because many of the systems that run on desktops, these systems will also run on laptops, which depend on battery. So it's a similar scenario to applications running on smartphones. And why am I mentioning applications? Well, you could say, yeah, but it's the hardware who really consumes energy, who really uses energy. And yes, it's true. But at the same time, it's the software that drives that hardware to consume energy or not. Current hardware is really good at not consuming a lot of energy when it's idle. So it's to a large extent the software's fault. And energy is also important for data centers, as you will probably be aware. In a relatively outdated estimate that I read not long ago, about 1% of all the energy in the world is consumed by data centers. But for developed countries, figures are a bit bleaker. I don't know if that word exists, bleaker, because in the Netherlands, for example, about 2.3% of the energy consumed comes from data centers. So that's a lot of energy. And as I said, it's driven to a large extent by software and by the way software behaves And it's not a coincidence that developers also care very much about energy efficiency. And a number of researchers throughout the years have shown that again and again in different contexts. And the thing is, even though software developers care very much about energy efficiency, there's a small catch, which is these developers, they're really smart people. They know a lot about how to build software systems. They understand frameworks. Sometimes they understand a lot of design as well. They understand distributed platforms. They know a lot of technical stuff, but many of them, and that's based on research that we and others have conducted, they really don't know that much about how to make software more energy efficient. And that's where we come in. We want to help these developers to remain as much as possible not very knowledgeable about energy efficiency, because we want to give them tools and knowledge that will enable them to build software that is more energy efficient in a cheap way. And, you could tackle that problem from many different perspectives. One of them is that these developers, they have to make a bunch of small, very fine-grained decisions about how to implement different parts of the systems they build. Because these the different options involved in these choices have different energy footprints. And developers must make really a large number of these decisions. And, they can't really worry about energy efficiency at such a small scale, but we can. And that's our starting point. We can help them make decisions about what is a good choice to tackle a specific fine-grained problem, such as the selection of a linear data structure. So should you use, in a language such as Java, an array list or a vector or a linked list? What's the trade-off? So that's where we come in. And in this work, I'm going to focus specifically on collections because they are nice to illustrate this idea, although this applies to other contexts as well. And collections are not only useful to illustrate this, but collections are also in widespread use. They're used very frequently in very many software systems. And we have run a query on GitHub about uses of the Java Euro collections library. This is the basic Java library implementing collections such as associative collections like hash tables and maps, or sets and lists, vectors, this kind of thing. And these collections are in widespread use. They are used very frequently. As you can see, we have array list which appeared more than 35 million times. And even if you look at thread-safe collections, which one could think are maybe not used that often, maybe, I don't know what's your intuition about this, but vector, for example, is used very often as well, more than 4 million occurrences. Hash table, almost 2 million occurrences, and this is a bit outdated. So these numbers are most certainly bigger right now. This is a query that we have run like 2 years ago. So it's very outdated, arguably. And so our main proposal is that, the high level idea is to look at these specific decisions that developers can make about stuff such as thread management constructs, or color themes, or data structure implementations, or concurrency control mechanisms, input-output primitives, to look at these issues and help developers to make smarter decisions while imposing as little extra work as possible. And, collections, again, are promising in that regard, because if we look at those numbers from that table, we will see that in Java, the vast majority of the uses of collection implementations, they come from very few classes. So they come from array list, HashMap, HashSet, vector, and hash table. So these are very few collections, and unless they are super efficient in every possible scenario, there is a lot of room for improvement there, because we can just try alternatives. I mean, we have only within the Java language, we have like 24 different collection implementations, maybe 30 or so. So it's a big number, and therefore we have many alternatives. And we have conducted a lot of studies in this sense. So this is not out of nowhere. We have seen this again and again, situations where if developers have had made different choices, they could have improved the energy footprint of the systems they build. And so I don't mention input-output primitives or concurrency control in vain. We have looked at these aspects. We have looked across different languages like Java, JavaScript, Haskell, C++, and we have seen this over and over. So this is why we are tackling this problem. So what is our proposal then? Considering this context, what is our proposal? Well, we start from a scenario where there are many alternative implementations of programming constructs. So for example, for lists in a language such as Java, you have array list, you have linked list, you have vector. So just one small issue is that we separate thread safe from non-thread safe collections because they are used in different scenarios. Thread safety is nice, but it imposes a very heavy performance and, in our experience, energy consumption overhead, whereas these other collections provide less guarantees but are more efficient. So we look at a scenario such as this, and we create what we call, we didn't create this term, we just adapting it, just using it, what we call energy profiles. So what is that? Basically, we collect information about how the operations in these concrete collections perform in terms of energy efficiency if we run them a lot. So we look at operations to insert elements for a linear data structure, because we have different kinds of data structures. So for a linear data structure, we look at the performance of these collections when we insert elements in the beginning, when we insert elements at the end, when we get an element from the middle or remove an element from the middle, for collections that are full of elements or collections that are empty. So we exercise a number of different scenarios in a completely application independent way and gather these measurements that we're not interested in the values themselves, but the values give us ground to compare the performance of these operations, of these collections, for each different operation. Because, for example, a linked list is very efficient for insertions in the beginning, but not so much when you try to do it in the middle. At the same time, an array list is nice if you just want to replace an element by the other. However, if you want to remove an element, it's a nightmare because it will involve a lot of copying data around. So these collections have different characteristics for different operations. So we obtain this data, the profile data, which is application independent, but platform dependent. So of course, it depends on the current version of Java or an operating system. So it depends on specific characteristics of the underlying platform, because these things change between versions of the language, for example. And we also examine the application. So the application that one wants to optimize. I'm saying application in a very broad sense here. So the software system, it may be a library. So it doesn't need to be an end user application. So for that, we perform what we call a usage analysis, which basically consists of, in our current approach, of statically analyzing the program so as to try to gauge how often are these collection implementations, such as array list here and here, used, and whether they are used within loops or recursive functions. Because it's too naive to just look at how often these operations are used. It's silly, actually. However, if you look at that, while accounting for the fact that an operation is used within a structure that performs repetition, So you have a hint that maybe that use of that specific collection is a bit more heavyweight than in another place that is not within a loop. And of course, we don't look just at the collection implementation and whether it's using a loop, but also we look at the operation that is being performed within that loop, because that will be taken into account in the third phase where we combine these two pieces of information, the energy profiles, which are application independent but platform dependent, and the usage data, which is platform independent but application dependent. So we, perform some calculations that don't really matter that much. You don't need to understand this formula. I just want to show you it exists, and emphasize that we consider the energy for uses of collections that do not come from a loop and that appear within a loop. That's it. So we combine these two pieces of information, and that will give us grounds to make recommendations and to tell the developer, you shouldn't be using Hashtable here. You should be using this other collection implementation because it's much more efficient. And I mentioned Hashtable because Hashtable, informally, it's reasonable to say it sucks. It should never be used in Java, the Hashtable class. There are much better alternatives within and outside the language libraries. And we implement this approach in a tool called CT+. It leverages the Wala toolkit for static analysis to gather information about energy efficiency. CT+ works on Intel platforms, so it uses REPL, which leverages some performance counters that exist within Intel architecture machines that provide us with information about, amongst other things, energy consumption of different parts of the machine, of the CPU, RAM memory, and Uncore, and also use Android battery stats, which uses modeling. It's not really hardware based, but some studies have shown that it's fairly accurate. So this tool works with both infrastructures. It works for both applications that run on Intel machines and Android applications. And the tool works with 40, actually it's 39, this number is wrong, sorry, I forgot to fix it, collection implementation, so it's a bunch of them. It organizes the collection in collections as linear data structures, associative data structures, and sets. It also separates them between thread safe and thread unsafe. We have taken particular care in examining the documentation of these data structure implementations, these collection implementations, in order to ensure that we do not make recommendations that, according to the documentation, could change program behavior. So this is one of the reasons why you won't find, for example, weak hash map here, because weak hash map has the sometimes undesirable property of just letting data be garbage collected by Java's garbage collector, by Java's memory management infrastructure. So this is not good if you need the data to be guaranteed to stay in memory. For caching, this is fine. But if you need consistency, that won't fly. So we have excluded some cases of collections that could lead to weird behavior, even though they're actually pretty efficient. Weak hash map is fairly efficient. So we have taken some collections, not just from the Java collections framework, but also from Eclipse collections and from Apache Commons collections. These are very mature collections of collections, let's say. And we have evaluated this approach by conducting a study targeting these two research questions. To what extent can we improve the energy efficiency of an application by statically recommending Java collections, and whether these recommendations are device independent? Spoiler alert, they're not, because of mobile devices. And we have conducted this evaluation on 7 different machines. 7 is not a very big number, but yeah, it's a lot more work than it seems. So I'm making excuses here because yes, that's the case. So 2 laptops, a powerful server, and 4 mobile devices, 3 smartphones, 1 tablet, We have some variety in terms of execution environments. So even though it's only a few devices, as I said, it's a fair amount of diversity. And for the methodology, we run a bunch of micro benchmarks that enable us to collect the energy profiles, the application independent, platform dependent part of our approach. We run them many times to get reliable data. We also execute these software systems that we have analyzed, these 16 software systems, many times, 30 with and 30 without the recommendations proposed by our tool. So we just take the recommendations and apply them automatically to simulate a scenario where a developer would not judge like hundreds of different recommendations, because that's not very cost effective. The workloads for these applications, they vary. Some from the Da Capo benchmark suite, which aims at supporting experiments in performance and in performance analysis. Some of them come from tests that are associated to these systems, and others we had to create by ourselves. And yeah, this is the configuration of the application. So, I mean, it's a bunch of applications. You won't probably even remember this. The thing that I'd like to emphasize is that we could not run all the applications in all scenarios, sometimes because in all the machines, sometimes because it doesn't make sense. Like I can't run Tomcat on a mobile device, but Tomcat is a web server, in case you're not familiar with it. But also because we did this in more than one step, and in the meantime, the versions of Da Capo changed. Some of the benchmarks could not be run on a machine with a certain configuration. So at the end of the day, we had this Dell laptop where we ran these 7 not benchmarks, these systems. These are real systems. 2 of them we run on the server as well, because we think this fits the profile of a server better. On the mobile device, we ran these 2 very small applications. Some of them are actually more like libraries. In all these platforms, we ran these 3, and we also run 4 additional applications that appeared in a later version of Da Capo on this newer, more powerful laptop. And I don't expect you to read this table. This is just to show you that we have results, we have conducted statistical tests, the data is in the paper. But in summary, what I can say is, for the desktop machines, I mean the 2 laptops and the server, for every app, we obtained an improvement by using this approach. And for every case, the improvement was statistically significant, most of the times with a medium, high, or very high effect size. So these are reasonably trustworthy results as far as performance analysis goes. And, you know, you can see here that some of the improvements were considerable. So for this GraphG system, we had more than 10% reduction in energy consumption after applying the recommendations from CT+. Of course, there were some cases where the improvement was smaller, although still statistically significant. And for many cases, we had, you know, good improvement, like more than 4%. And this may seem like not a lot, but you have to bear in mind, this is completely automatic. No developer was hurt in this experiment. No one needed to actually implement these modifications by hand. This was all done by the tool, just by replacing collections. So this is considerable. For the mobile devices, results were a lot less encouraging. So you can see very few results here, because these are the ones where we had statistical significance. And effect sizes are generally smaller, although not small. And for some cases where you see a negative percentage here, we actually had a worsening of the energy consumption by using CT+. These are not big increases in energy consumption, like the biggest one was 1% or something. But yeah, it's still not negligible. And as you can see, it is very clear that these results are not device independent, because for the same benchmark, for the same system in 3 different devices, we had a very big improvement, a very slight worsening, and a small but bigger worsening. So yeah, you can have it all. Smartphones are really hard because of the effect of the battery. Battery creates a lot of inconsistency. And yeah, this is just to illustrate this a little bit more. So we had benchmarks like Zeeland, where we had pretty consistent improvements. We had systems such as Extreme, where we had reasonable improvements on the Dell laptop and no improvement on the mobile devices, no worsening either. And we had an example such as Commons Math, where we had very big improvement in one mobile device and, worse energy consumption in another one. So yeah. And just one thing more I like to emphasize about this experiment is that most of the cases, the recommendations come from outside the Java Collections framework. So for the desktop machines, more than 90% of the recommendations to use either the Apache collections or the Apache Commons collections or the Eclipse collections. So, and as you can see, these originally, on the right-hand side, you can see the recommendations. And on the left-hand side, what they used to be, what these systems used to use. So it was mostly array list, hash map, and hash table. And so, yeah. And for mobile devices, we observed a similar, though less accentuated trend, where most of the recommendations were suggested the use of collections from other libraries, from Eclipse or from Apache, but there was a stronger presence, let's say, of the Java Collections framework. And right now, we are proceeding with this work, although at a slightly different direction. We're looking at multi-platform frameworks that support the construction of mobile apps that run on multiple different platforms like iOS, Android, Windows, Linux. There are quite a few of these frameworks, and they are in widespread use in practice. So what motivates us to do this is that since these frameworks are so popular and so many apps are built on top of them, if you improve them just a little bit, you can affect apps potentially in multiple different scenarios. Of course, as I said, the improvements are not platform independent, so take this with a grain of salt, but it's still something that has potential for impact. And so far, we have conducted some experiments using some of the benchmarks from the computer language benchmarks game, which is a website that aims to compare the performance of different programming languages. And we did that for React Native and Ionic, which are 2 of these frameworks. And what I can tell you from this graph, you probably are asking yourself where you should look. What you should look is at the right-hand side and look at the bars of the same color on top and in the bottom. And if you see very different numbers, then it suggests that this is worthwhile research. And the numbers are actually very different, because React Native is consistently really bad when it comes to both performance and energy efficiency. No, it's not directly proportional, as you can see, but it's very consistently bad. So this got us really excited to look at other frameworks such as Flutter. And I also work with code readability and code understanding. I love that topic, and error handling, but I don't have time to talk about that today, maybe in a future colloquium. So for now, I thank you for your attention. And yeah, I'm open for questions. Thank you.
First, let's start with a round of applause for our speaker.
Thank you.
All right, so this is really interesting. Do I understand correctly that the main idea in the proposal is that you're actually going to recommend the coders to change things? I mean, the last benchmark you showed, it was all automatic, but it's not supposed to be the default mode, right?
No.
Yeah. So, and then...
Just let me elaborate a little bit on this.
Yes.
Because there are some cases where it seems to be safe to do it completely automatically. I haven't shown you this, but there were some cases of collections that were dominated by other collections.
Yeah.
And what we mean by this is that for every, you have two collections that are of the same type, like two maps, for example, and for every operation of one exhibited better, lower energy consumption than the same operation for the other one. Every operation. So in these cases, it's fairly safe to use the one that dominates instead of the one that is dominated.
But you're looking at this from an energy perspective. So,
yes.
And that's probably very much correlated with the space and time complexity as well, I suppose.
Yes.
But is it also correlated with cognitive load on the programmer? Because some data structures require a little bit of maintenance, right? I mean, that could, and as the programs that we write became more and more complex, the cognitive load on the programmer becomes an important issue. So people prefer simpler data structures just because it makes the program more readable and more. So can we say that it's a good idea to? I mean, I can perfectly understand the argument when this is done automatically in a transparent way to the programmer, but when it comes to recommending the programmer some stuff, then I'm not sure
that's
whether
the thing.
Yeah.
That's one of the things. Java is a very criticized language. It's very in fashion to say bad things, to talk, to say bad things about Java. But Java's collections are designed, in my opinion, in a very nice way, so that for almost every collection, if you program to an interface, this reminds me of my software engineering classes, the lecture that I gave yesterday, actually. If you program to the interface of the collection, in most cases, it's just a matter of changing the concrete type of the object that's being instantiated. You don't change anything else. There's no extra cognitive load on the programmer. And we actually check that. If the programmer uses features that depend on a specific implementation, we do not make that recommendation. Because that would break behavior preservation.
Okay. First Vishnu, then Christian, then Frank.
Okay.
Vishnu?
Hi, thank you. Thanks, Fernando, for the presentation. Hi. So I have maybe two closely related questions. So the first one is that when you show the graph, there seems to be a pretty strong correlation between optimizing time and optimizing energy. So to say, if I can throw away a loop and therefore reducing my number of operations, and therefore I will also reduce the energy that I use. So the question is it always like that? And the second question is whether we also look at other way of reducing the energy. For example, if I'm pumping a lot of operations in short time, then the CPU will heat and the fan will start to activate. I don't know how much energy that will cost, but it does cost something. So maybe by delaying the operation, then I can optimize a little bit at the cost of time. So I wonder whether that's a thing in energy consumption.
Yes, although we don't look at that. But yes, definitely, because there are many different sources of energy consumption, and we can't cover them all. But about so I don't have a good answer for the second question. About the first question, though, I do. And in most cases, you could say that optimizing for performance leads you to optimize for energy efficiency. That's true. What we did notice, though, is that when you add concurrency to the mix, it's not as clear cut as it may be, as it is for a sequential scenario. So if you permit, I just want to show you this scatter plot. So this is from another paper. It's about energy consumption of Haskell with a specific focus on thread management constructs. And when we look at threat management and concurrency control constructs, and what these scatter plots show is energy along one axis and time along the other. And if we have a perfect matching between these two, all the points will be along the diagonal. And when we examine data structures in Haskell, purely functional data structures, which are not thread safe, that's exactly what we see. All the points are laid along the diagonal, but that's not the case when you have some kind of concurrency. So it depends on the system, basically. There is a strong correlation. There is always a correlation, and it's never weak, but sometimes it's not very strong. Okay?
Okay, interesting. Thank you.
Sure.
Christian?
Yeah. So thanks for your talk. I mean, I would have like 10 billion questions to talk and discuss with you, but I'm limiting myself.
We can have a chat later.
Yeah, exactly. I would really like that. So because I'm also talking in my course on computer architecture and operating systems about the combination on and impact on energy efficiency. So I'm really interested in that. So now, in your proposal, you talk about collections used in a loop, and I like absolutely agree with you on that, on your point. My question now is, did you, and if so, how far, consider the impact of hardware caching effects? Because on the one hand, it's something that you would probably want, but on the other hand, it also may skew your measurements, right?
I haven't. I mean, what we have done is, and you would say that it's probably very naive from an architecture, a researcher on computer architecture's perspective, is that we run the benchmark a number of times in order to have the data that is frequently used in cache, if that applies. But if you're working with a very large collection, that won't matter very much because you have too many cache misses anyway.
So on the data part, the question is more like, so for example, if you run those applications and they are bound to certain like libraries in the background in Java that use the same interface, then they would share memory pages, right? So they would reuse them, and therefore you would have caching effects. Or do you use separate libraries that hence do not share memory pages and hence limit the amount of caching effects?
I can't tell if they share memory pages or not. I can't, because we haven't looked into that.
I think it would be interesting.
What we do is when we run a benchmark, that the class for that benchmark, I mean, if you're talking about the instructions, will be loaded as soon as Java is loaded, because that's how Java works, unless you're dealing with dynamic class loading. But we only load that one to reduce overhead. So we don't. Having said that, depending on how you import, I don't know how that works, to be completely honest, because depending on how you import,
to discuss at some other
multiple
point.
classes will be visible, and Java may load all of them. So I had never thought about that.
You're starting a new project, the two of you, I think.
Hopefully.
Just a detailed question. The same thing goes with like swapping on servers. So you say you benchmark it on servers. Now, like if you benchmark it on a laptop, you can run into swap, which is very nice, but it's not allowed on servers. So is there any impact on that regarding energy efficiency, benchmarks?
I didn't get your question, Christian.
So for swapping, right? If you run a big benchmark, you can swap out memory pages, right?
Okay.
Which
no, we did not worry about that on the server because we ran it on a server that had way more RAM than we needed.
Okay, cool.
So yes, it's a practical consideration, but for the server, it was a machine with like more than 100 gigabytes.
Yep.
Very powerful machine.
Sufficient. Thanks.
Frank, thank you for your patience. Please unmute yourself.
That's okay. Yeah, I think in part my question was the same as Vishnu's, but so maybe following up on that. So for the cases where sort of performance time performance was not correlated with energy efficiency. So I mean, can you say something more about those cases and like were they because of a specific data structure? I mean, are, for example, hash maps typically maybe slower but more energy efficient, and if so, why? Or
there was one case, the short, very short summary, the one sentence response is, sometimes you get performance by being wasteful. That's the summary. But I can tell you an example that does not come from this specific work, because we were not really looking into that in detail for this specific work. But from another one where that one where we looked at Haskell, there was this benchmark called FASTA. It's from the computer language benchmarks game. We love that site because we have some benchmarks there. They're very well optimized. So they're very nice to perform this kind of study. And FASTA was an interesting case because the configuration where we executed that had the best performance was also the configuration that had the worst energy consumption. And why was that? Because it used transactional memory for concurrency control. And transactional memory is an optimistic concurrency control mechanism. So it basically never stops trying. And it tried a lot. So when we performed some profiling of what was going on, we got this full bar where all the processors of that server, that 20 core server, were being used at the same time. So it was very high energy consumption because it was wasting resources trying to commit transactions that were being successfully, not successfully, it's the other way around, that were being aborted in sequence, but at the same time, it was still making progress because there were so many threads running. So it was basically wasting resources, but it was faster than all the alternatives. So that's an example. And that's a case where correlation between performance and energy was medium.
Fernando, does the temperature of the environment kind of influence? I mean, if you run the same algorithms at different times, will you get a different energy profile?
I assume so, but at the same time, I've ran all these benchmarks were run in a city that is very close to the equator. So you don't have a lot of variation in terms of temperature. No, I'm not joking, because if you go to a data center room, it's usually freezing.
Yeah.
So, but that's, so you don't have a lot of amplitude of breath in terms of temperature, but probably yes, because as highlighted by Vishnu, you get your fan running, you dissipate more heat, which is basically wasted energy. So probably yes.
So if you repeat the whole experiment with servers that are kept at a very low temperature in a room, you might get different answers. Is that what you mean?
You might get. Okay, this is a wild guess. Okay, so bear that in mind. But you might get results that are different, but specifically for the context of servers, of machines that do not require a battery, or at least are not running on battery, you know, if the underlying environment in terms of Java version, this kind of thing, because the implementations change through versions, I think you would not get very different relative results, because the results were very consistent across the different machines for the desktop environment. There was very little variation. Standard deviation was really low. We got these very small p-values because there was so little variation. So, you know, I would assume you would get maybe different results, but not different relative results, which are the ones that really matter, I think, in this context.
And then one more question, which I think is important. Like at the moment, two of the important energy losses are caused by running deep learning solutions and Bitcoin mining. or cryptocurrency mining in general. Have you ever tested those algorithms for efficiency?
I'm looking forward to working along those lines. This is something that I would like to tackle. Ideally, not in the long term, but in the short term or medium term. But for Bitcoin mining, I'm very okay. I'm gonna come out and say I'm very ignorant about that. But I do know that part of what makes it work is being wasteful, depending on the strategy you use, if it's proof of work or not. So, when I look at that, I get a bit disheartened about the possibilities because of these inherent things that are in a way political and economic and that I have no control over. For machine learning, however, I do see a lot of ground for improvement. I was talking about this today in the morning with colleagues who are actually here, like Cici. So maybe, there's room for that. A paper was just accepted at a conference, at a major conference in the area of software engineering, ICSC. It's not by me, but where the authors just compared two different deep learning frameworks, TensorFlow and PyTorch. And the results are different. And not only are they different, because this is boring, of course they will be different, but they are different in interesting ways because some have better energy efficiency for some kinds of classification problems, and others perform better in other problems.
Yeah.
So I'm still looking forward to reading the paper. The authors haven't made it available. I just talked to one of the authors on Twitter.
Yeah, it's very interesting. Roland.
Let's see, yes. So I'm working on multi-agent systems, crowd simulations. And so this is an example of a high-performance system. And we noted that we got a lot of optimizations by changing memory allocations and by programming in such a way that memory allocations aren't done very often. And there we obtained a speed up of 100 times on a 64-core machine. And many of those optimizations, I think, can be done automatically. Are you also considering these kind of optimizations?
No, because so far, almost all the work we have done has focused on managed languages where you don't do memory allocation by hand. They don't even allow you to, like at least not that I know of, like Haskell or Java. I mean, Java will tell you that it's got an interface for the garbage collector, but that's not true. It doesn't really work like that. So they are mostly managed languages. So there's a lot of room for that, because if you control a memory allocation, you also control the garbage collector, which is this background component of the infrastructure that keeps eating away at your CPU and stopping all the work from going on while still consuming a lot of resources. So yes, that's a nice path, but I'm assuming you're using a language, and maybe I'm wrong, that's where you have to do it by hand, at least to a certain extent.
Yeah, so we are in this case using Rust.
Yes. So, yes.
And but one of the tricks is to reuse objects instead of destroying it and renewing it. And I think this is also a way of coding instead, a way of programming that you can adopt to. And maybe also some automatic translations can be done to find some patterns. And for instance, I saw that in one of the examples on the first sheets you show, examples of memory that is being allocated, which is not needed. So maybe there are some gains there, I think.
Yes. Okay, two examples that come to my mind. First, when this is not something that we have studied, but in Swift, for example, when you build table views, it's common practice to reuse the objects corresponding to the cells, because that saves you from having to deallocate and then allocate again. So that's a common practice. That's the first example. Second example, some work we have conducted in the past on Java, actually. It's not really about allocation, but it's related, where we identify that it's common for applications that use the fork join framework which is an important part of Java. It's not very widely used by applications, but applications use streams which use fork join. So it's very common for applications that use fork join to, when performing a computation on big amounts of data, where you partition the data to create copies of the data. And that's killer, because the copies are expensive and you have a lot of additional allocation and deallocation. So we actually implemented a tool to refactor software to perform that in place, that operation in place, precisely to avoid that kind of overhead. So it makes perfect sense. It's just a matter of which language you're working with.
That's also a good example of the cognitive load issue. I mean, garbage collection, if you're going to do it manually, that means more cognitive load. You know, it is more efficient, but the programmer needs to do more work. Yeah, you know, find clever ways of saving memory allocations or slower I/O operations, for example. Very nice. Any other questions? Vishnu, anything from your side? Because I saw you.
Oh, yeah, I can pose a short question.
Yes, please.
Maybe any advice. Well, I mean, asking advice. So okay. I use Java a lot, but I'm not claiming to be a good Java programmer. So there, I use...
Nou, ik kan morgen wel enkel even kijken hoor, want het zijn dan nota's van de spoor 2 en van spoor 1.
Shall I continue?
Yes.
Right. So I use stream a lot. So when you have a collection and then you want to do map and filter and you convert it into a stream and then you do your operations and then you collect it again. It seems to be the recommended way of doing stuff since, I don't know, Java 10 or something. But of course, we can do everything using an explicit for loop. Do you happen to know if that would be better in terms of energy?
I have never studied streams specifically, so I won't even make a guess. I know that they impose some levels of additional overhead. Of course, there's the cognitive load issue that Albert has raised, but I have no opinion or data on that. So I'll refrain from making guesses. I don't know.
So do you think we can use your framework to measure our project?
We could probably adapt it. I mean, it will be a little bit of work to add the appropriate static analysis, but it's not sophisticated from a static analysis standpoint. And yes, this is actually we have contemplated doing. We just didn't have the human power to do it.
That would be nice.
Yes, definitely. I find it lots of fun.
Okay. I'll contact you later on.
Sure.
Thank you very much, Fernando. You see, it's raising a lot of potential new projects. Let's have a final round of applause for our speaker.
Thank you, folks. Thank you for all the questions. Thank you for the participation. I'm really happy. As I said, my first time at the department colloquium, so I'm really excited.
Thank you. So let's meet next week, same time, same place. Bye, everyone.
Bye. Take care. Stay safe.